Hello and welcome back. Today I want to tackle an interesting problem that was brought to my attention by a viewer, Mr. Kieran Jeffries. And this problem involves feedback loops and system stability. The problem being, how do you simulate the loop response of a circuit to figure out if it's stable or not? So if you're curious about open loop and closed loop simulations, as well as how to perform these simulations in both linear and switching circuits, then keep watching. So let's start off by analyzing what's the difference between an open and a closed loop circuit. So what I got here is a simple single transistor amplifier. This is a good example of an open loop system, since signal comes in one way and goes out the other, and none of the output signal comes back to the input, so there's absolutely no link between the output and the input. Now we can simulate this, and this is basically the typical AC type of analysis performed in LTspice. You've got your output gain plotted with a solid line and the output phase plotted with a dotted line. And this is in reference to the input signal, which I've got right here, so this AC1. Now we can go into a deeper analysis with our amplifier and see exactly where all these inflection points in the gain come from. So we can see that right at the beginning we've got a high pass filter, and then at the end we've got this higher frequency behavior modification. Now the question comes, is there any part of the transistor circuit itself that is giving us a low frequency effect? Now we can see that by analyzing what happens between node number 3 and our output, node number 2. And to do this, to analyze two different nodes other than the reference signal, we simply need to take our node that we wish to analyze and divide it by the node we wish to compare it to. So in this case, I'm going to divide the voltage in node number 2 by the voltage in node number 3. And this time we can see that we have a perfectly flat response at low frequencies. And we can conclude that this low frequency nonlinearity comes from the initial filter. So basically, this is the way to analyze ratios of signals in an AC simulation when you don't really want to analyze the reference AC signal. So not the signal that you're actually injecting, but two signals inside your circuit. Now another thing to keep in mind when doing such simulations can be highlighted with this example. So right here I've got an op-amp configured as an amplifier, and this time I'm injecting the signal through a 1 farad capacitor, so it doesn't have to be a realistic capacitor. And I've done this just to eliminate any sort of low frequency misbehavior. Now we can see that since I've got the 1000 factor amplification, I get 60 decibels. So exactly what we expect. Now watch what happens if I increase this. Let's say I want 10,000 factor of amplification, so 80 decibels of gain. This time I get minus 10. Now that's not even close to 80 decibels. So what happened? Well, to get an idea, we need to understand how this AC simulation works. First of all, LTspice will calculate the DC operating point of the circuit, meaning that it will consider all capacitors as open circuits, all inductors as short circuits, and then just run a DC simulation to see exactly what are the voltages in the system. After the stable operating point has been obtained, then the reactive components are added and a very small AC signal is injected as requested. Now the problem that we see in this circuit is that we have a problem in the DC operating point analysis. That is because this circuit will not work in a normal transient type of simulation. Why is that? Well, we're trying to amplify by a factor of 10,000, and we should be able to do this, but we've failed to take into account that this op-amp has a bit of offset voltage. So whatever offset it has, we've amplified it by 10,000, and it probably ended up saturating the output. So it either gave us a saturated positive output or a saturated negative output. But when we take a lower gain, like 1000, then everything works perfectly fine. We have not saturated the op-amp and we can proceed with our AC analysis. So if you want to perform any AC simulations, first make sure that the circuit actually works and it doesn't just lock up. And you can do this by performing a transient type of simulation. So you can switch between these two simulations when performing your circuit analysis. You need to make sure that inserting an AC signal is a realistic request to which the circuit can actually respond. The same is true when the circuit is finished. You need to verify the results with a final transient simulation to make sure that, again, everything is still stable. So that about covers open loop type of circuits. But that's not really what you were interested in, right? You wanted a closed loop. Now, before moving forward, let's take a moment to look at what exactly are we supposed to obtain from a closed loop simulation. What are we going to look at in the phase and gain of the closed loop system? So as an example, I prepared these two graphs. We've got a gain graph expressed in decibels and the corresponding phase graph. Now in LTspice, both of these graphs are plotted on exactly the same panel. What I did is just to keep things a bit more visible and a bit more clear. So what do we need to look at? What are the important parameters that we need to extract from these two graphs? Well, the first thing we're interested in is the crossover frequency. The frequency at which the gain crosses through the 0 point into the negative region. So when gain goes from positive to negative. This parameter is important since it will tell us how fast our loop is. Up to what frequencies can it actually work? If you inject a signal that is of higher frequency than the crossover frequency, then the loop no longer has any gain to respond to that. So your circuit will only be able to work with frequencies lower than this crossover point. The next thing we're interested in is also related to this crossover point. And that is, what is the phase of the response at crossover frequency? Now, why is this important? Well, we've got two extremes we need to consider. If our response is 180 degrees, then we've built an oscillator. If we inject a signal at this frequency, then our loop will give us an inverted version of that signal. If we insert the inverted version, then it will give us a non-inverted version, and so on. So basically, if our phase at crossover is 180, we've built an oscillator. We don't want that. The other extreme is 0 degrees. If we inject a signal, we get the exact same signal. If we inject a bit lower frequency, then we're amplifying and amplifying and amplifying, and basically we've built a positive feedback system, which again is something we don't really want. What we do want, on the other hand, is a stable system. And we can get stability only if our response is around 90 degrees. Now, in practice, you will not get perfectly 90 degrees in all cases. I mean, you can get it, but it's not always that easy. So the next parameter we're interested in is the phase margin. How far away are we from creating an oscillator? Now, as I said, ideally we want this phase margin to be 90 degrees. But depending on the industry you're working in, acceptable values might range from around 80 for aerospace industries down to about 45 in commercial applications. So in general, closer you are to 90, the better. So is there anything else we can extract from here? Well, there are a few more things. Now, as I said, if you get to 180, then you've built an oscillator. So the next thing we're interested in is, when you actually do get a phase of 180, when your system would work as an oscillator, what's the gain? Now, what we want in this point is to have as low a gain as possible. So to have a high gain margin. Again, depending on what you're working on, the exact value will differ. But in general, more is better. And that's about it. Or is it? Well, there's one more thing you need to be aware of. Although you have a crossover frequency relatively low, components in your system might be able to work at higher frequency than that. So it's important to generate this feedback loop measurement up to a frequency at which you're absolutely sure that your circuit can no longer have any sort of gain. And that's important because in some cases, depending on how your system is built, it is possible for the gain after the initial crossover to increase again, up to a point in which it crosses over 0. Point at which, again, you have a crossover frequency. So why is this a problem? even in this graph, we can see that at this point, we already have extremely high phase in our system. So we can get a very stable first crossover frequency and a very unstable second crossover frequency. And basically, these are the things you need to look at when you're performing a loop stability analysis. Now let's see these parameters in our simulation. So how do you analyze a closed loop system? Well, LTspice gives us a few examples in the examples folder. So loop gain and loop gain 2. So let's look a bit at these. Now one way of performing this analysis is to simply look at the voltage gain. So you interrupt your feedback loop, add in your AC voltage source, and then simply plot out the ratio of the two voltages. So let's see what happens if we do this. We get a nice response, we can see the gain slowly decreasing, but we get a bit of a problem. At one point, the gain starts to increase back up. And this is not something normal, so this is not something that happens in real life. But if we go back to the example, LTspice actually tells us that to measure the gain of this circuit, you need to take this massive formula into account. Now if we plot this formula, then we get something a bit more realistic. So you can see with blue the new massive formula in which the gain is roughly identical up until a point where it's no longer identical. So the gain decreases down to infinity. So with increasing frequency, the gain is smaller and smaller. And this is a far more realistic type of simulation. So when performing closed loop simulations, it's not enough to just measure the voltage ratio, but you also need to take into account the current. Reason being that into one end you inject a signal and then you measure the response on the other end. That's how you perform the open loop simulation. Now here, by adding a simple voltage source, if we look at the current through it, we can see that it starts to increase. So you no longer have the same ideal infinite impedance on the input always. Some current with increasing frequency starts to pass through. That's because of the capacities of the inputs. So to correctly model this, you can use this massive formula. Or, in the second loop example, they're using this sort of circuit, in which you measure both the voltage and the current gain of the circuit at the same time, and then plot them out using this massive formula. Now we can see that the second massive formula gives us exactly the same response as the first massive formula. So they're both good, difference being that in the first case we needed double the circuitry, in the second case we need only a single circuit, but we need some fancy parameters and a quite an interesting formula. Okay, so is there any other way of doing this, a way that's a bit more simple than this? Well, there actually is, and I've got it right here. So what I've done here is I've opened the closed loop not by adding a voltage or current source, but by adding an inductor, a 1 terahenry inductor. So this is completely unrealistic, but the simulator doesn't care. Basically what this will do is isolate the op-amp's input from the output. And then I'm injecting my AC signal through a 1 terafarad capacitor. So what kind of response do I get from this thing? And we can see that with my nice simple formula, we're getting almost exactly the same as with the really complicated ones. There's no major difference between the two. That is because by including this massive inductor, we made sure that there's no current going through our loop. So we've completely isolated the inputs from the outputs. So which one is best? Well, depending on how much time and effort you want to put into this, you can use any of the three, not the first one. So simply adding an AC voltage source and measuring the voltage ratio between and after it is not good enough. I mean, it will be good until a point, but after that it will no longer be accurate. So at low frequencies it's good, but not at high frequencies. And especially if this thing needs to drive any sort of load. So let's just see what happens in all of these circuits if I add this output load to it. Now if we simulate, we see that things start to become a bit different. So the very first way of measuring simply voltage ratios is completely bad. So the higher the load, on the input of the circuit, the worse the response will become. So you can see that gain flattens out at around 30 something dB, so completely unrealistic. Now, the inductor version isn't that good either. So we still see that there's a certain mismatch between that measurement and the complicated formulas. So again, although this method is simple, it's not always the best. So this will only work well if it doesn't have to drive any sort of load. So if you're interrupting your loop in a point in which you've got a high impedance input. Otherwise, you will have problems with it. So my recommendation is either take one of these complicated versions or use the inductor capacitor version, but make sure that there's no load attached to it. And basically this is how you would simulate closed loops in linear systems. Now that's all fine and dandy, but how would you do it in a switching system? Now with a switching supply, you can't really perform an AC type of simulation, since there's no DC operating point. You need to perform transient simulation. So let's see how we can do that. So to highlight the method of generating the loop reaction of a switching supply, I took the test fixture circuit of the LTC3412 that is provided by LTspice and then added a voltage source to it. This is of course after explaining how this way of measuring is not the best. But anyway, I did not come up with this example. I actually found it online on Analog's webpage, in which they explain how to extract the loop gain from a switching power supply. And this article isn't written by anybody, it's actually written by Michael Engelhardt, the creator of LTspice. Now it's a great article, I highly recommend that you go through it, it contains a lot of great information, and let's just run it to see exactly what it does. Now the simulation takes quite a lot of time, and I started it up so that I can explain some things in the meantime. So how does this work? Well, we're performing a transient simulation, of course, and we're performing multiple runs of the transient simulation. And we've broken the feedback loop by inserting this voltage source into it, in which we will insert, let me just full screen this, in which we will insert a 1 millivolt AC signal at various frequencies. Now the frequencies are varied from 10 kHz to 1 MHz in a decadic fashion by simulating 3 frequencies per decade, and that gives us a total of 7 frequencies to simulate. We're performing a transient simulation in which we run the simulator for 900 microseconds, but only start saving data after 700, since the first 700 are needed just to get the power supply up and running. And then we're using this options statement to remove any sort of compression, so plot when size equals 0 means that we will not compress the data, and we will be using numbers with 15 digits, so to have maximum precision. Now you can also use this statement, the .save statement, so that you don't overload your computer memory, but I found that this isn't really necessary. Now the magic happens with this thing. So all these measurements, these are needed to generate the frequency and phase diagram of the loop response. So we start by calculating the average voltages of the two signals, and then we extract the real and the imaginary voltage for each of these in each of the simulations. So that's what this part is used for. And then finally we calculate the ratio of the two. So to calculate the voltage gains magnitude and the voltage gains phase difference. So quite interesting mathematics. You can go through it, you can play with it. It's quite nice. Now at the same time as I'm simulating this, I'm also simulating the exact same circuit in which I'm adding a load pulse. And the reason for doing this is to show how the circuit actually responds in a normal transient simulation, so without adding any sort of perturbation, to see if the data that we're getting is actually correct. So the simulation is done. How do we extract the data? Well, if we look at any of the node voltages, we won't see anything useful. I mean, we see a lot of colors and some oscillations, but this isn't really a Bode plot. To do that, we need to go to the error log. This is where all the measurement data is highlighted, and then simply right click and we need to plot the stepped measured data. Now we get this question regarding complex data, and yes, we do want to write this as complex data, and we get another window which is expressed according to frequency. And here we need to add our trace that we measured, which is the voltage gain. Now in the measurement, we didn't actually have a voltage gain measurement. We had the voltage gain magnitude and the voltage gain phase difference. So you could have written anything here, so call it Bob Mag and Bob Phi. Simulator doesn't care, but maybe you like it like that. And then the simulator knows that it's the same exact parameter, but first you're introducing the magnitude and then the phase. So now we can add this trace, voltage gain, and we see our loop response for our measured circuit. And we can have a look at the crossover frequency, so when the gain goes through 0, and we see that it's at around 130 kilohertz, and that we have a phase of 14 degrees, which is horrible. But is the loop stable? Well, this is why I put here the second simulated circuit, which is exactly the same as the first one. Here we can actually look at the output voltage, see what's happening. Now the simulation ran 7 times, that's why there's so many things going on here, but we can see some very interesting things in this simulation. First of all, the voltage before applying this pulse, so the load pulse, wasn't exactly stable. So we do see that there is a small oscillation in it. So not the small ripple, this is from the switching, it's the larger ripple, which is the average voltage, which is not perfectly stable. Secondly, we can see that when we applied the load pulse, the voltage didn't cleanly return. It had this oscillation built into it. So the loop design in this circuit is not perfect, so it needs some work. And the closer you get to a good phase margin of around 90 degrees, the better it will work. And that's about it. That's how you should simulate feedback loops in switching supplies. So even though this voltage injection method isn't the best, as long as you take care of how you use it, so you connect it to a high impedance pin on one side, like the feedback pin, it will give satisfactory results. The other methods, like including a 1 terahenry inductor and so on, will not really work in this case, since you will not be able to perform a transient simulation, but this method is good enough. And in general, these are the methods through which you can simulate the closed loop response of a circuit, both for linear systems and for nonlinear systems. So, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.